Good. Today we want to introduce the three cumulants, the most important combinatoric object in free probability theory. So we saw in the last lectures that we want to write moments in terms of other objects, which we are calling free cumulants, by a formula which is given by a summation over non-crossing partitions, and then for each such a partition we have a multiplicative contribution in terms of products corresponding to blocks. Okay, and last time we looked a little bit into combinatorics of non-crossing partitions. They form a poset, so we have a partial order, and so we have the general theory of Möbius inversion, and today we use this to define the free cumulants. So right away we define those objects. Okay, so the setting is, of course, we have a non-commutative probability space, A phi, non-commutative probability space, and then we want to define the cumulants by Möbius inversion of the moments, but in this setting we needed functionals, moment functionals, so this means I need a functionals indexed by n. So I have to make out of my one linear function which I have here, I have to make some phi n's, but this is done in a very canonical way. So namely, then you put phi n of a1, comma, up to a n equal as the moment, this is just Jens' moment of those guys, and this is just phi of the product. So this is just phi of a1 and so on up to a. So here I'm just multiplying the a's, but here I make functionals out of them in all those arguments. So phi n should have n arguments, and this is defined just by taking this. Good. Okay, so this is now a collection of those multilinear functionals which we had last time, and then we can extend this in a multiplicative way to phi indexed by one non-crossing partitions. So this, so we extend this to the corresponding multiplicative family. Functionals, which are now not just indexed by natural numbers. I mean, those essentially correspond to the functional which are indexed by the maximal element in NC of n, but we want to have that indexed by any non-crossing partition of any size, and so this is just done by this multiplicative extension. So phi pi, if pi is let's say n is a natural number and pi is a non-crossing partition. So we need this pi for all of them. So pi is a non-crossing partition an element. So pi should have n arguments. Okay, so the a's are just elements from A. Of course here, all these a's a1 to an are elements from our algebra. And here the same. So those are elements from the algebra, and one is phi. This is the product of the corresponding phi n's. The product is running over the blocks of pi, and for each block of pi, we take the corresponding moment of the elements which are connected by this block. So this is phi of, here I have the number of elements in the block, and then I take the variables, a1 up to an restricted to v. Right, so this denotes, I'm just choosing of the variables here, so many variables which are corresponding to the block V, which are connected by this block. So we do this for n. Okay, as I have here. Good. Okay, and also I have now my moment functionals, and now I can define the cumulant functionals by Möbius inversion. So I can now take essentially the convolution of this is the Möbius function, and what we get there we call the free cumulants. So corresponding they are defined via Möbius inversion. So they are defined by the formula kappa is the convolution of phi is the Möbius function. And of course, now we have to take into account, I mean, that those are not just ordinary functions going to C on our poset, but they are functions which are actually functionals. But of course, the formulas are the same. So this means that, let's say, kappa sigma of A1 up to N is given by summing over all pi by non-crossing partitions. Okay, if I have here the argument sigma, I'm only summing over those pi which are less or equal to sigma. And then I take phi pi, also for each pi, I take phi pi of the elements A1 up to AN. So this is a product of moments of the guys here corresponding to the block structure, and then I multiply with the Möbius function, so mu of pi comma sigma. Right, that was the general structure of our convolution. Before we had it just for ordinary functions, but now we also have to distribute those moments here. Okay, so this is for all non-crossing partition sigma with n, of course for all n, and of course the a's are just arbitrary elements in our algebra. Elements in A. Okay. Good, so that's a definition of our cumulants. And now, of course, the phi's are multilinear functionals. And of course, on the structure of the formula, it is clear that the kappas are also multilinear in their arguments. And of course, the phi's, I have made a multiplicative family out of them. And now we expect that, of course, also the kappas, which are defined like this, they should also be a multiplicative family. So the kappa sigma, of course, should be a product of the kappas corresponding to the blocks, because that's exactly what we have if we do the formula the other way around. Okay, but I mean, this should follow from this definition, and that's what we want to see in the next proposition. So let's write this down, the proposition. So the first is just the linear structure. This is clear. So namely, each of those kappas is multilinear. So each free cumulant functional kappa, let's say I, goes from A n to C. So it has n arguments. If pi is n, then this is multilinear or n-linear object, so it's linear in each of its n arguments. So this is and I mean, this is clear because of this formula and because each of these 5 pi's is linear. As you see, phi n, of course, is linear in each of those guys here, and in this product here, again, it's linear. Good. Okay, so this is clear, but maybe the second point is maybe not directly clear, but also true. So namely that the family of all those kappa pi's is actually also multiplicative family. Family kappa pi of pi in non-crossing partition. So this is also multiplicative, and this means it's determined by the value if the pi is the maximal element in the corresponding NCN. So it's determined by kappa n's, which are just the kappa corresponding to the maximal element in NC of A. And then in general, kappa pi is just the product of the corresponding kappas like this, corresponding to the block structure. Good. So the proof. I said, one is clear. Since all the 5 pi's are multilinear, and the structure of this formula. So since all are multilinear. Good. Okay. So for 2, we have to understand. We have to see that essentially the multiplicativity of those guys, and you should think about multiplicativity of this, goes over to multiplicativity of this. So what we have to prove is we have to look on a kappa sigma for sigma and arbitrary non-crossing partition, and then see that this decomposes into the product of the corresponding kappas for each of the blocks. So let us consider such a kappa sigma. Let's say kappa sigma of A1 up to An. And the sigma, we should write down blocks explicitly because we want to see the decomposition into blocks. So sigma, let's say, is of the form it has blocks V1 up to VR. This is a non-crossing partition of n elements. So sigma has R blocks, which we denote by V1 up to VR. Good. Okay, so now in the definition of my kappa sigma, I have to sum over all pi's which are less than this sigma. Okay, but I mean the non-crossing partitions which are less than the sigma are quite easy to understand because I mean this partial order means that each block here is contained fully in one of the blocks here. Actually, I mean I get the blocks from here by decomposing blocks from here into smaller blocks. And of course I have to do this in a non-crossing way. So this means if I want to find the pi's which are less than this, essentially I have to look for each block of the sigma here, and then I mean taking the non-crossing partitions of this block. Okay, so this means that each pi which is less than sigma actually decomposes into a product of non-crossing partitions of the blocks of sigma. So I have to sum over such pi's, so I should understand that better. So any pi which is less or equal than sigma decomposes actually into a union of non-crossing partitions, one for each of the blocks of the sigma. I can write this as a union of P1 up to PR, where the PR are non-crossing partitions of the block PR. So I mean, P has some blocks, and the blocks of P are subsets of the blocks of sigma. Okay, so in pi 1 I'm just collecting the blocks of pi which are contained in this block V1. In P2 I'm collecting the blocks of pi which are contained in V2 and so on. And of course, I mean, it's clear that I mean the blocks of pi must be non-crossing. And I mean, if I take any non-crossing sub-blocks of the V's, I respect the general non-crossing condition. I mean, I cannot get a conflict between a different V's because the sigma is non-crossing. Okay, so I mean, there's no crossing between the blocks of sigma. So for the pi's, I just have to make sure that also inside the blocks I don't have crossings. Okay, so this means any such pi decomposes into this, and of course anything of this form is really non-crossing partition, which is less than the sigma. Good. Okay, and so this means that the interval over which I'm summing here actually decomposes now into a product of very easy intervals. So I mean, summing over all pi's, which are less than sigma, actually is now just the task of summing over all each of these pi 1 up to pi r independently within the non-crossing partitions from 0 to the maximum element 1. Okay, so what I'm saying here is that the interval sigma also decomposes. accordingly into the product of intervals corresponding to this decomposition. So pi sigma, that's this is equal to the interval from pi 1 and the one element of V1 cross and so on, the interval P pi r 1 of VR. Okay, good. Now, so I have to see, so why am I interested in this interval? So I have to see, of course, I'm summing over those pi's, and I have to see that I have multiplicative factorization here. Of course, this phi is multiplicative. So if I have the structure of the phi, this decomposition of the phi pi, I have a multiplicative factorization. I also have to know, does this also factorize in a multiplicative way? Okay. And so this is the mu function from pi, comma sigma, and we know the Möbius function only depends on the interval between pi and sigma. Okay, so that's why it's good to know that this interval from pi to sigma, all non-crossing partitions between this and this actually factorizes into this product. If I want to have a non-crossing partition between this and this, I need a non-crossing partition for the first component. So this must be a partition which is between pi 1 and the maximal block, because sigma in this decomposition corresponds just to the block V1, and so on. And then I need a partition between this and this. Okay, and the posset structure also goes over to this. So if I have a product of posets, then of course the partial order is a component-wise partial order. All of them have to respect the order. Okay, so this interval factorizes into this, which is element in the non-crossing partitions of V1 times and so on, non-crossing partitions of VR. Okay, but this means that we also get a corresponding factorization of the Möbius function, because the Möbius function only depends on this interval, so it only depends on the structure of this interval. Because that was also the recursive definition of the Möbius function. The recursive definition, if I want to define the value of the Möbius function at pi and sigma, it only looks on information on elements which are in this interval. The rest of my poset doesn't play a role for this. So if I understand this interval, then, and I see that this interval actually has this nice form, then actually I get also a factorization of the Möbius function. So since value u of pi comma sigma depends only on interval between those 2 points, interval from pi to sigma. This was the recursive definition of our Möbius function. So this cognitive point was by recursive definition, which we did in 3.5, where we showed that the Möbius function exists, and we showed it essentially by defining it in a recursive way. Okay, so we have that the Möbius function only depends on this interval, and furthermore, the Möbius function of this guy is the Möbius function of this guy, because I have an isomorphism between this, so every product here goes over to here. And the Möbius function of the product of intervals is just the product to Möbius functions. That is something which is quite easy to see. So you should think a little bit about this, but this is hopefully clear. Okay, so the Möbius function here actually is the same as if I calculated on this side, but here I have a product, and the Möbius function of the product of posets is the Möbius function of this is the product of the Möbius functions. So and Möbius function of a product of posets the product decomposition of the Möbius function of this point pi and sigma. Okay, so this mu of phi sigma, that's what we need in this formula, actually decomposes in a multiplicative way into the Möbius function of this interval times and so on times this interval. So this is the Möbius function of pi 1 up to the maximal element, and so on. This is the Möbius function of pi r up to the maximal element, of course in the smaller non-crossing partitions. So this is the Möbius function of pi 1 up to 1, v1, and so on. Möbius function of pr up to 1. Okay, so essentially, I mean, yeah, we are just looking over pi's which are smaller than sigma, and then essentially we can decompose the problems into sub-problems for each of the blocks of sigma. And everything factorizes in a multiplicative way, because all those problems are independent of each other. So what I do in one block of sigma doesn't really affect what I do in another block of sigma. Good. Okay, again, we can go back to this formula and plug in this information which we have, and hopefully get then also the multiplicative decomposition of the kappa. Good. Okay, so here this. Okay, so we have this factorization, but we use it for the Möbius function. Here. Good, so let us now take the formula which defines kappa sigma and do the multiplicative decomposition of all quantities which we have here. Okay, so we want to see that kappa sigma A1 to an decomposes as a product of the kappas corresponding to the blocks. Okay, so by definition this is the sum over pi and nc n, where pi is less or equal to sigma, and we have phi of pi of a1 up to an multiplied with the Möbius function of pi sigma. Good, okay, but now we know this each pi less or equal to this can be written as this union of pi's of pi 1 up to pi r. So this sum here is actually the sum over pi 1, which is a non-crossing partition of the first block of sigma, up to pi r, which is a non-crossing partition of the last block of sigma. Right? So we are summing over those guys independently, and these contributions here factorize very nicely with respect to this. So I mean, pi is now the product of those guys, and of course this is multiplicative, so this factorizes into contributions of phi for each block, for each block of pi. Some of those blocks give me pi 1, some of them give me pi 2, and so on. Okay, so I mean I can just regroup the factors, and what I get here is actually now the product over blocks over I from 1 to r, where I just have phi of pi I of a1 to an restricted to this block vi. So this means, I mean, this is a product of all the blocks which I have in pi, but I'm collecting now. Some of the blocks are in pi 1, some of the blocks are in pi 2, and so on. So I'm just writing this as a product like this, and of course, I mean, the a's correspond to the ones which go with the vi. Okay, but we also know that the mu here factorizes also as a product corresponding to this block decomposition. This here is also the product, this product also applies to this. So this is also the product of the mu of pi I and the maximal element we have this proposition, and now of course what I have here, written in a different way, is changing the product of the sum. I'm taking the product over all those terms, and for each of them I have a sum where I'm summing over pi I, non-crossing partition of vi, and the contribution here which I have is just this field pi I, a1 to the n, restricted to vi, multiplied with the Möbius function pi up to the second argument is 1 vi. Yeah, okay, but I mean if I'm now doing this sum here, this is now nothing else than having my formula which defines in the kappa for the kappa corresponding to this partition here. So this here is nothing else than kappa is the number of elements vi a1 to an restricted to vi. Yeah, maybe better I should write the kappa corresponding to the one partition for vi. So by the same formula. This is just the formula if I choose for sigma the partition 1 for the interval vi. So you see, everything factorizes into the corresponding sums for each of the blocks of vi, and I get here just the product of all those. So what I get, continue writing down here. So I get in the end is really the product over the blocks. So I mean this is the product over the blocks of sigma. The product over the blocks of sigma, and for each of the blocks I get the contribution, which is given by kappa 1v, but this is just the kappa, it's the number of blocks of v. If I use so you define the kappa of n. This is just the kappa of the one partition. Okay, so we get this of the base restricted to v. That's the end of the proof. So it's just simple calculation, just using the fact that of course this is multiplicative, and maybe the only other crucial insight is that the Möbius function here is also multiplicative. Okay, and then this multiplicativity goes over to the other side. Good. So then maybe we make a few remarks, and then maybe also look on concrete forms of our cumulants. Okay, so that's the general formula. We define the few cumulants by the Möbius inversion of the moment functionals, but of course by Möbius inversion we know that this is equivalent by saying that the moments are given by summing over the cumulants. And that was the structure of the formula which we observed in our limit theorems. And of course, I mean, this Möbius inversion is just solving those equations in a recursive relation. So maybe. Also by Möbius inversion, our definition of the cumulants, cumulants are given by taking the convolution of the moment function, this is the Möbius function, is of course equivalent to saying that the moment function is given by the cumulants convolved with the zeta function. That was the form which usually we observed in the last chapter. And the point is that we can solve this for the cumulants. Okay. And all this, I mean, we do not only have just in general Möbius inversion, but we have functions which are multiplicative. I mean, both the phi and the kappa are multiplicative. And I mean, here we have seen, if we have formulas like this and we assume that one is multiplicative, then the other is also multiplicative. Okay, so I mean, we can also say more precisely that the free cumulants are determined. Free cumulants are determined by the facts that we have a multiplicative family of objects at kappa pi, and C is multiplicative, and that we have this relation here between phi's and kappas. And that we have, and if this is a multiplicative family, I mean, I only have, and also the phi's are multiplicative family, I only have to know the phi's, let's say, on the blocks. So that we have for all n and all arguments. These are just general arguments of our algebra A. That I have this relation. So this is equivalent to this. So that I have phi n of A1 up to AN. But I mean this here is of course nothing else than phi A1 multiplied A2 and so on up to AN. Okay, so this is just a moment essentially of those variables, and this given in terms of the kappas by summing over the non-Prosy elements in n. And if I have here n, I have here the maximum element 1n, so the summation here runs over everything. So usually I mean I'm summing over the guys which are smaller than the index which I have here, but here I have the index 1n, which is the maximum element in the CFN, so I'm summing over everything. And here I have the of okay, so this is the formula which actually we had in the last chapter. Good. Okay, so our kappas are determined by this formula by doing Möbius inversion. And of course, at the moment we don't really know the Möbius function of the non-Gaussian partitions, so maybe for really calculating a few kappas, we should just explicitly do the inversion of this formula, and by this also getting some values of the Möbius function. I mean, of course, we could try to calculate in general what is the Möbius function of mu of pi sigma for the non-Gaussian partitions, but I mean, there's no really very explicit general formula, so this is not so clear. Of course, we can derive a lot of properties and some formulas for this, but very often it's not really important that we know the actual value of the Möbius function. It's more important to know the structure of the formula. Okay, in a sense, this formula is nicer than the other way around, because this doesn't involve the Möbius function. This involves the zeta function, which is 1. I mean, all the coefficients here are 1. Here we know there are some other coefficients, but maybe which we don't really know so exactly. So I mean, if one does proofs, maybe it's also sometimes maybe easier to use this formula. Or this formula without really, it's not so important what the actual values of mu are. Good, but in any case, I mean, those relations between cumulant and moments are very important, so maybe we also give a name to those formulas, so we just call them moment-cumulant formulas. Also, if I address the moment, if I talk about the moment-cumulant formulas, I mean either this or this. Convolution of the moments with mu, and the other way around, the moments are the convolution of the zeta function, which are in definition for this this reformulation, and Möbius inversion are called moment-cumulant formulas. Good. Okay, so this is just a name, and maybe now you really should look on concrete examples. I mean, we have to find the cumulants abstractly. Maybe we should really see concretely what they are. So let us do 2 examples. So I mean, the cumulant functionals are multiplicative, so only need to know the kappa n. Corresponding to the maximum elements, and let us calculate a few small ones. Of course, the formulas are getting bigger and bigger because we have to sum over nc of n, which is growing fast, but at least for small n, one really can do it. So, and of course, we could say we calculate somehow the Möbius function in these lattices, and then we use this formula, which is the convolution with the Möbius function. Or what we are going to do now is we just take this formula, which says the moments are given by summing over the kappas, and then we solve this in terms of the moments. And then, of course, we see the value of the Möbius function in those formulas. So let us calculate some n. Explicitly inverting isolation of phi is given by taking the convolution system. Okay, so the simplest case, a very simple case, of course, is n is equal to 1, because what does this formula here tell us? It says that, let's say, phi of a1, which of course is the same as phi 1 of a1, so phi 1 of a1. So n is now 1, so we have to sum over non-crossing partitions of one element, but of course there's only one such non-crossing partition, and contribution. So what I have is a kappa, which is indexed by, so this is the partition of one element, which only has the one block, the 1, and this of course only one block, so this is kappa 1. Okay, so this just tells us that kappa 1 actually is nothing else than our original function of phi. So phi kappa 1 of a1 is just phi of a1. And of course, I mean, we know that we have to write kappa as a product of our moments, so the coefficient which we see here must be the Möbius function from 1 to 2. So here, this tells us that the Möbius function from this to this is equal to 1. This is the one crossing element. So NC of 1 is only one element. So there's only one value of the Möbius function there. And this is of course 1. But I mean, that's what we know. So actually, from this knowledge, we would see this. Good. Okay, so for n equal to 2. There we have the phi of a1 in 2, which is our phi 2 of a1, comma 2, and this is now given by summing over non-crossing partitions of two elements, and there are two of them. So I get here a sum over two terms, one corresponding to the block, to the partition which has one block, a1 in 2, plus kappa corresponding to the other partition of NC2, which has two singletons, A1, and of course this has one block, so here I get a kappa 2, A1 and 2. Here I have two blocks, so I get a product of the contributions for each block, and I have a block of size 1, this contains the element A1, and I have another block of size 1 corresponding to A2. Okay, so this gives me this formula, and now you see, of course, I can solve this for kappa 2 because I already know kappa 1. That's exactly the Möbius conversion which I was doing abstractly. In this structure of the formulas, I exactly have one highest order term and lower order terms which I already know by induction. Okay, so explicitly this tells me that kappa 2 A2 is phi of A1, A2 minus this term, but the kappa 1s are just the phi. So this is minus phi of A1 times phi of A2. Okay, and abstractly we know that this is given by summing over all partitions, multiplicative contribution of the moment, and the coefficients are the Möbius functions. So what we see here, this coefficient, of course, this is the coefficient from here, from largest to largest. This must be 1. So the highest order term always has 1. And this here, this minus 1 here, this is the Möbius function from this to this. So this tells us this is minus 1. Of course, essentially, what we are doing here is essentially solving the equation for the Möbius function. If we still have these kappas and phis around, I mean, doesn't really matter. The same calculations you would do if you want to calculate the value of the Möbius function. Good. Then for 3, and that's the last one I'm doing, because then I have to sum over 5 terms. It's still okay. The next would be summing over 14 terms, which I don't like to do. For 3, I have the product of 3 terms, phi of A1, A2, and 3, which is our phi 3 of A1, A2, and 3. And this is given by summing over non-crossing partitions of 3 elements, and there are 5 terms. So what I get here is the kappa of this. Of course, I have the arguments, which I will not write in a moment. Also, kappa is this kappa of this, is kappa of this, plus kappa of the last one, which only has 3 signals. Okay, and of course, I mean, we know that this factorizes. This, yeah. Which I have there, factorized into a product of kappas for blocks, and then it is the correct distribution of the arguments, of course. So this, what I have here, so the first one has only one block, so this is a kappa 3, which contains all the arguments. Then the second guy has one singleton, which corresponds to the A1, and then a block of size 2, which connects the A2 and the A3. Then I have correspondingly a kappa 1 of A2, a kappa 2 of A1, A3, plus a kappa 1 of A3, and a block which connects the first and the second element. And the last term, this has 3 blocks, so I have a product of 3 kappa 1s, so I have kappa 1 of A1, kappa 1 of A2 times kappa 1 of A3. Oh, okay, and this, the sum of this, is equal to this moment. And again, I can solve this for kappa 3, because I already know kappa 1 and kappa 2 in terms of the phi. So I can express the kappa 3 in terms of the phi's, and if you do this, yeah, of course you will get many terms, there will be some cancellations or something. So, but what you get in the end should be again the sum, which is a sum running over non-crossing partitions, corresponding contribution of the moments, factorizing in a multiplicative way, and some coefficients, which are the Möbius functions. So if you do the calculation here, also you will get that kappa 3, A1, A2, A3 is given. Of course, the highest order terms is phi of A1, A2, A3, and then we have minus phi of A1. So we have corresponding factorizations like the kappas, phi 1 of phi of A2, A3, minus phi of A2, phi of A1, A3, minus phi of A3, phi of A1, A2, and then we have plus 2 times phi of A1, phi of A2, phi of A3. So you see the sum here, and of course the coefficients which I have here are again the Möbius function. So that I have a 1 here is because the Möbius function of the 3 to 1, 3 is 1. It's always. The same elements here, we know the Möbius function is 1. So here, what I have here is the coefficient mu of this partition, which is this, going up to 1. So we always have the Möbius function. The second argument is always one block of the element, and here we are just running over the factorization which we have here. So you see that this here is -1, and here the same. This is mu of this partition, also -1, and here in the same way, -1 here is the mu of this, this. So I mean I have here the phi, which corresponds to this, phi of A1 and 2 times phi of A3. This is also this. But here you see, you can also get something else. It's not just having plus or -1, but we get a 2 here, and this is the Möbius function where I go from the smallest element to the largest element in NP3. And this is plus 2. Good. Okay, so you see the coefficients, if I write the formula like this, they will always be integer numbers, but they have a sign, and the numbers can grow. Okay, so it's knowing explicitly what the coefficients are, maybe it's not so clear in general. If I do it the other way around, like this, then the coefficients are always 1. It's just a zeta function. Okay, it's the same information. Good, and maybe, yeah, so now, I mean, those are the general formulas, but maybe we should also now use the knowledge which we have about specific distributions, and up to now we have a semicircular element and a Poisson element. Maybe we should also reformulate this in the language of cumulants. What does it mean? What is the value of the free cumulants? Okay, so that's maybe part 2 of this example. So what can we now say about the free cumulants of the semicircular element? So that SB, let's say a standard semicircular element. So this is the most important distribution or element in free probability theory. It's the analog of the classical Gaussian variable. So what does it mean to be a standard semicircular element? We defined this in 2012, but it was defined via the limit of the central limit theorem, right? It's the element which we get as the limit in the central limit theorem, and there we saw that what we get has special moments, namely the even moment, the odd moments are 0, and the even moments are just given by counting the number of non-crossing pairings of 2n elements. If I want the 2nth moment, I have to sum, I have to look how many non-crossing pairings do I have of those guys. And of course we can write this maybe in this summation formula. So essentially I'm summing not over all partitions now, but only over the non-crossing pairings of 2m, and then I get a multiplicative contribution of each pairing, but the contribution is just 1, which you can say is the product of having 1 for each of the blocks. So each block has a contribution 1, which means the whole contribution is 1, and then of course I'm just summing over all of them, which means I'm just counting them. Okay, so we already have here more or less our Moment-Cumulant formula. The only thing is that we are not summing over all partitions here, over all non-crossing partitions, but only over the pairings. But of course, this can be taken into this formula into account, that we are saying, okay, I mean the contribution of a non-crossing partition, the contribution of a block which does not have size 2 is 0. And then we could write down this general formula, but effectively we are only summing over the non-crossing pairings. So this means we have exactly here this formula summing over all the non-crossing pairings, and we have a multiplicative contribution. And this multiplicative contribution is exactly of the form that a block of size 2 has contribution 1, and a block of a different size has contribution 0. And so this means that the free cumulants of the semicircular element are just 1 if I'm looking at the second cumulant and 0 otherwise. So from this formula, you see that the cumulants, it's cumulants, the cumulants are always with free cumulants here, are the form kappa n. I mean, if I'm saying I want cumulants of a semicircular element, when the kappa n's are linear functional, so I can plug in elements from my algebra, each argument. But if I'm saying I want to look on the cumulants of S, this means I'm just plugging in S. No? So I just take the cumulant where all the arguments are S. The same way as I'm talking about the moments of my element S, I'm just looking on phi applied to power of S. And phi is also a function I can apply to any product of any elements which I have in my algebra. But if I'm talking about the moments of S, I only want to apply it to products of S. And so if I'm talking about cumulants of S, I only apply the kappas to this S. And in this case, this formula tells us that this is 1 if n is equal to 2. So the second cumulant of a semicircular element is 1, but all the others are 0. And maybe let me write down again that this fits with this structure here, this formula, because if I define the guys like this, then the multiplicative extension does exactly what it should. So namely then, the corresponding multiplicative extension of this. So this is kappa pi of S. All the arguments are S. Oh, okay. So and pi is now arbitrary non-crossing partition of n elements. So this is by definition given by the product over the blocks of pi. And for each block, I take the contribution of the cumulant corresponding to this block. So I'm putting in the argument, I'm putting in the variables which correspond to this block, but now all the arguments are S, so it doesn't really matter. I mean, I'm just plugging in everywhere S's. So I just have here kappa of number of elements in the block, many guys, and the arguments are just S. And now with this definition, or with this, we said that the cumulant is only different from 0 if this guy here is equal to 2. So this is just delta. The number of elements in the block is 2. Then it is 1, otherwise it is 0. And so this means in this product here, if I want to get something, each term should be 1. I mean, if one of them is 0, the whole thing is 0. So I can only get 1 if each term is 1, but this means that the number of elements in this block must be 2. Which means what I get here is exactly 1 if all the blocks have size 2, which means I have a non-crossing pairing, and it is 0 otherwise. So this is 1 if pi is not arbitrary non-crossing partition of n elements, but actually pairing, and 0 otherwise. Okay, and then of course, I mean, this fits with the general formula here. No? So I mean, you can really now write this as the sum over all pi in nc of n, and that would be a kappa of pi of the s's. This is this kappa. So this kappa is really a solution of this equation, because by Möbius inversion we know the solution is unique, so those must be the cumulants of the semicircle. So this gives the right value, which gives the right value for the moment. By Möbius inversion, we know that the kappas are uniquely determined, so if we find a multiplicative family of guys which satisfies this formula for the moments, those must be the cumulants. And Möbius inversion this. Good. Okay. And in the same way, of course, we can now see what the free cumulants of a free Poisson element are. Because we also, we essentially define them in terms of their moments in formula like this. So free Poisson distribution, this was the distribution which we get in the limit of this law of square events. So the analog of the classical limit theorem, which gives you the classical Poisson limit. And there we had a formula like this. So we sum over all non-crossing partitions, and the contribution of such a guy was actually lambda to the number of blocks. And this, of course, fits again very nicely with this and tells us exactly what the cumulants are. So, in the same way, the description of the moments of a free Poisson, and let me take here free Poisson parameter lambda, the free Poisson, let's say element x of lambda, positive lambda. So we define this in 218. So by giving the formula of the moments, so the moment of the free Poisson of parameter lambda, the kth moment, this was given by summing over non-crossing partitions of k, and then each such partition makes a contribution lambda to the number of blocks in pi. If lambda is equal to 1, then actually, this is just 1, and then we are just counting the non-crossing partitions. But for general lambda, we have contributions like this, but of course you see that this fits now again very nicely with our formulas. So then we have here a sum over nc of k, and this contribution here really is multiplicative in the blocks. Because you see, I have here lambda to the number of blocks, which means each block makes a contribution lambda. So I can also write this as the product over the blocks of pi, the contribution of each block is lambda. The size of the block doesn't play a role. They are all the same. And now, of course, this is exactly the formula which we want, and here I should have the kappa n. So this tells me all the cumulants of Poisson are the same, they are all equal to lambda. So this tells us it's cumulants, it's three cumulants form x, so all arguments in my cumulant functional are this x, and these are all equal to lambda for all n. So particularly if I have a standard free Poisson, which means lambda is equal to 1, then all the cumulants are equal to 1. Good. Okay. So this was some examples about this. And now we want to continue to look a little bit more on properties of these cumulant functionals. Cumulant functionals, they are linear functionals in algebra. We have an algebra from which we have our random variables, and we defined those kappas. And we know they are multilinear. So the linear structure is clear. But the question is, how do they relate with the product structure in my algebra? For the phi's, this is very simple. This is associativity. But for the kappas, this is not so clear. And this is not as simple. It's not just associativity in some sense, but it's a reformulation of this, and we have to understand this, because this is a very important general formula, which is important for many exercises. So, for the remark, let me just raise the question which we want to consider and solve it in the following. So with respect to the additive structure of our algebra, okay, both, essentially the moments and the kappas are multilinear. So the structure is clear. So this is back to the additive structure. Now pi are all multilinear functions. Good, okay, but what we also have to understand is what happens if I multiply two of my argument, of my elements, and maybe put them in as arguments. Can I understand what happens on the level of the cumulants? So we need to understand also the behavior with respect to the multiplicative structure. So really the multiplication of A, not just the multiplication is real. It's real complex numbers. I mean, this is also clear. Multilinearity also tells us that we can take this out. But what happens if I multiply in my argument some elements from the algebra? Okay, so we also have to, we should understand the behavior with respect to the multiplicative structure. Okay, and I mean, the cumulant functionals are defined in terms of the moment functionals, and for the moment functionals, this is easy. Because this is essentially means that the commas are not really important. I mean, when I wrote phi n, I put commas between my arguments, but this was actually a phi where I multiplied the arguments. And I mean, the commas don't really play a role because of associativity. So for the moment functionals, this is just associativity. Follow sense when you make this clear. What I really mean is this example. Also, what I want is I want to consider my phi n's or my kappa n's, so they are functionals which have n arguments, and I am asking the question, what happens if I multiply in my arguments? I put in a product of guys. So this means, for example, I can take phi 2, the first argument is actually a product of two guys, and then I have a second argument. Also phi 2 has two arguments, but the first is a product, and the second could also be a product, but let's say it's just an A3. The first thing is, I mean, this product here, what does this mean? But of course, I mean phi 2, so this is just a phi where I multiply those guys. So here I'm multiplying the first argument, which is A1 and 2, is the second argument. But of course, I mean, associativity tells me, I mean, I can put brackets here as I like, so I can also write this as phi of A1 multiplied with A2 A3, and this would be then phi 2, where the first argument is A1 and the second is A2 A3. Or I could also write in the form where I don't put brackets at all, and I just say this is a product of three guys, and then it would also be the same as phi 3 A1 A2 A3. So you see, I mean, those guys are all related, and actually, I mean, the comma here is just because I want to say this is a two-linear function. I can put commas arbitrarily, I can erase them. So the comma and doing multiplication is more or less the same. Good. But now if I do the same for my cumulants, of course this is not true anymore. So there the situation is not so clear. But that's something which we want to understand. So if I do the corresponding thing for the cumulant, how about if I take kappa 2, and the first argument is, let's say, A1 and 2, the second argument is A3, then, I mean, we don't have associativity, so in general it's not true that this would be the same as just moving the comma from here to here. And this is not the same as A1, comma A2, A3. You should convince yourself, but just you have explicit formulas for this, so you should check this. Okay, so we don't it's not as easy as for the phi's, but the point is that there is a replacement. Of course, I mean, there should be some replacement. I mean, the phi's and the kappas, they are related by some nice formula. So if I have some properties of the phi's, this must transfer by moment-cumulant property to some property of the kappas. But the property might look different on this side. But the point is, it's still a property which we can write nicely and understand, and in particular also use later. Good. Okay, but so I mean, so we need some preparation for this, but that's the thing which you want to do. So maybe let me fix some notation just to fix the general problem which you want to consider in the following. So let's say, so what I want to do is, I mean, I want to consider a kappa, let's say of m arguments, but each of these arguments could be a product of other elements for my algebra. So I'm fixing, let's say m and n, natural numbers. Let's say n is less than n. So let's, I mean, m is the number of the products which I have, and n is the total number of arguments which I have. And I'm encoding this and saying, I want to multiply, I have indexing set which tells me how many arguments I want to multiply. So the first factor should be a product of I1. I multiply the first I1 guys, and then I have I2, and I multiply the guys from I1 plus 1 up to I2, and so on. And the last is Im, and this should be equal to this n. Okay. So maybe this becomes clearer when I write down the variables. So I consider now n variables, a1 up to an, in my algebra, and I multiply some of them together. So my products, I know by capital A's, so a1 is the product of the first I1 of those guys. So there I multiply a1, a2 to a1. So then for a2, I multiply, okay, I'm continuing, so I multiply the next one, which is a of I1 plus 1, and I'm going up to I2. So I multiply a I1 plus 1, and so on, up to a I2. Up to am, which is the product of the rest. So I'm starting at m minus 1 plus 1, and I'm going up to im. This im is just n. So those are the last bit of my class. Okay, and now we want somehow to relate the cumulants of this capital A's with the cumulants of this little a's. So we want to relate cumulants of the little a's with cumulants of the capital A's. Good. And again, on the level of, as I said before, on the level of the phi, this is very easy. No? And actually, but of course it means I have somehow to go over, I mean my formulas, if I go to cumulants, is a summation over nc of how many terms I have. No? If I'm looking at my elements as the little a's, then I have n elements, so somehow I should be nc of n. And if I'm looking on this capital A's, the products, I only have m, so I would be nc of n. So I must also relate non-crossing partitions from here with non-crossing partitions from here, which somehow have to do with the structure how I multiply these. So I mean, this is something which we see quite easily again on the level of the moment functionals. Because there we also want to, and we have our moment functionals indexed by non-crossing partitions. And so we should relate writing things in terms of the little a's with things writing in terms of the capital A's. So again, so we want, in the end we want to relate the cumulants of the capital and little a's at And of course, we have to do this by going via the moments, because the cumulants are defined in terms of the moments. So we have to use the corresponding properties for the moments. And there, as we already saw in the example, it's easy. So on the level of moments, this is simple. So namely, whenever I have, let's say, pi of NCM, those are pi's which correspond to the capital A's, then there is a corresponding partition which I call pi hat, which lives in NCN, which corresponds to the little a's, such that the moment functionals of pi, if I evaluate them at the A, is the same as the moment functional at the pi hat if I evaluate it at the little a's. So this means phi pi of A1, comma AM. So if I write something like this, I have m arguments here, so this pi should be in NC of m. But this I can also rewrite as a corresponding phi of the A1 up to AN. So I have here n variables. This means I need here a partition which is an NC of n, and but I say that is a pi hat, which corresponds somehow to this. Okay, and this pi hat, of course, can be very explicitly. So this is given by, so we have essentially, pi hat, we have to say what are the blocks, or which elements are in the same block. And of course, instead of saying I have a partition of 1 up to n, maybe it's better to say I have a partition of A1 up A2 and AN. I really use the A's as my set which I'm partitioning. So I should say when is AI in the same block with respect to pi hat as the J, and of course this happens if the AI corresponds to some product, capital A's, and the AJ is a factor in capital A, and of course these guys should be connected by p hat if they are connected via pi in the capital A's. So this means this is the same if, let's say, AI, let's say, is a factor of AP, it's a factor of one of them, so let's say of AP, and AJ is a factor of AQ, which might be the same. They might be the factor of both of them, of the same capital A, and then this AP and the AQ should be in the same block as pi. So if so any factor at AP and any factor in AQ, if AP and AQ are connected by P, those factors are connected by P. This is the thing about what we have seen there. This is exactly saying this here. Okay, so what we have here is an embedding of NCM into NCM. I have a mapping to each guy here. I associate a guy here, and this is a very nice mapping, which also preserves the structure of the poset structure, also the order. So if I have things which are in this order relation before, then if I put the hat on them, it remains the same order relation. So this hat mapping, of course, this depends on the special choice of the i's. So how many do I want to multiply? When I'm choosing the i's, then of course I have a different mapping here. But this is fixed before me. So this is an embedding of NCM into NCM. This is an embedding of posits. And maybe let us do an example just to be really sure. These are all kind of trivial statements, but maybe check a couple of things, and maybe the best is really to see this final example. So let us consider, let's say, m is equal to I have 6 little a's, and I multiply them together to 3 capital A's, and I do this in the following form. So A1 is just A1, right? I'm not multiplying anything. Yeah? For A2, I'm multiplying 3 elements together, so this is A2, A3, A4. And for A3, I'm multiplying the remaining 2 together, A5 and A6. So this is just a situation like this. And then we say we have a mapping which maps partitions, non-crossing partitions of the capital A's to non-crossing partitions of the little a's by just respecting somehow this multiplication. So I mean, we say A1, A2, A3. The partitions of these guys are mapped via this mapping to non-crossing partition of these 6 elements. And of course, I mean, I have here, I have here my usual 5. I have here 5 non-crossing partitions of those guys, and each of them is mapped to corresponding partition here. And what is this partition doing? I mean, this is essentially telling me which of the capital A's are connected. And then the A's which correspond to 1A itself, they are a priori connected. Of course, A1 is just here, so this is just this one. But then for the A2, this is here singleton, but here the A2 consists of A2, A3, A4, and they are connected on this side, because they are the factor of this A2. I mean, this definition here in particular tells me that if the A's are the same factor, the factor of the same capital A, then they are in the same block here. So this means this here goes to this, and the A3 goes to this. And now, if I start to have connections between the capital A's, then I have to connect the corresponding blocks here. So here I have A1 and A2, which means here I'm making this one, this stays alone. For this, I have this, and the other guys are connected. Here I have this singleton. The singleton is not the 3 block here, but the other 2 blocks which I have here are connected like this, and here everything is connected. Okay, and of course it is clear that this mapping here has exactly this property here. So maybe just should like this. I mean, that's really why this is a crucial mapping, because this is really the mapping which tells me how to rewrite the moment functionals of the little a's in terms of the moment functions of the capital A's. So this is really this mapping on the combinatoric level. So this will also play a role, of course, if I want to reformulate this property in terms of the cumulants. For example, this relation is, so if I look on phi, let's say of this partition, A1, A2, A3, so this is, by definition, this is phi 2, this is phi 2 of this block, but phi 2, of course, this is just doing multiplication directly, so this is phi of A1, A3 times phi corresponding to the singleton, which is phi A2. Okay, now I'm plugging in the little a's, so the capital A's. So actually this here is phi of, so what is A1? A1 is just little A1, and A3 is the phi A6, and here I have phi of A2, and this is A2, A3, A4. And of course you see what I have here is now phi of the elements A1 up to A6, space, so phi. Which partition do I have? I have the partition which connects 1 with 5 and 6, and which has 2 and 3 as a block. But of course, this is the mapping of this partition here under this guy. This mapping does exactly this inflation of partition here to partition here. Yeah, okay, so this mapping has exactly this property here. That's why we introduced it. And maybe a few more things which we observe. So you see we have a mapping from here to here, and you see that it somehow respects the maximal element. So the maximal element here goes over to the maximal element here. But the smallest element here, of course, is not the smallest element in NC6 here. Because I mean, the singletons here, each singleton here becomes actually a block which is of the size how many factors I have in the corresponding A. So this mapping has the properties, so note that the image of one of the maximal element in NC of M, so the hand of this is the maximal element in NCN. Okay, but for the zero, for the minimal elements, this is not true. So in general, the head of 0M is not the zero or the minimal element in NC of N. It's something which is bigger. And this is true as soon as N is different of N. Of course, M is equal to N is a special case, but this means I'm not multiplying anything. And then, of course, I just have the identity mapping from NCM to NCM. Okay, so if unless M is equal to N, then of course they are the same, but then I have trivial mapping. Then there's nothing to understand. Good. Okay, and maybe one should also observe that actually, if I'm looking on the set of all pi hat, for all pi with NC of M, this is actually, I mean, this is just the image of the interval from 0 to 1 in the M lattice, but this mapping here really is a coset structure, so this really gives me the interval from 1M, from 0M to 1M, which means, I mean, this is the largest element, but this means those are all the guys in NC of N which are bigger than this one. Those are all the sigmas in NC of N, and sigma is larger or equal to 0M. So all the guys which are showing up on this side in NC of 6 are the non-crossing partitions which are just bigger than this one. Because I mean, if I want to have anything which is greater or equal to this one, then what I have to do is I have to start connecting some of the blocks which I have here in non-crossing way. That's exactly what we are doing. But I mean, which blocks I should connect is already told by this one. So this here tells me all the possibilities which I have for connecting the blocks which I have here. So what I really have here is really just this set. Summing over all the sigmas of, this thing here is all sigmas which are greater than this. Good. Okay, maybe the last remark is that, as I already said, that this preserves the partial order. So I mean, tau goes to tau hat is mapping from one coset to another. Preserves the partial order. So this means, I mean, if pi is level equal than sigma, this also means that pi hat is level equal than sigma hat. Okay, and this means in particular that it also preserves the value of the Möbius function. Because the Möbius function only depends on order properties. And hence, in particular, if I want the Möbius function of pi comma tau in my, so if those are NC of M, then I can also get this as taking the image of those guys under this mapping hat in NC of N and calculate their values. So this is the same as the Möbius function of P hat and tau hat. This is for all pi and tau in NC of N. Yeah, of course, pi should be less than tau. That's only the Möbius function has no trivial value. Yeah, good. And of course, this will be important because I mean, the idea what we want to do is, of course, I mean, we want to relate the cumulants to the two lattices, but we know how to do this for the moment function, so we have to go to express the cumulants in terms of the moments. But I mean, then we also have to take the summation of a Möbius function, and if we want to relate things, we better know how we can relate those quantities to the two lattices which are involved. Because I mean, for one of the moment functions, we have to sum over non-crossing over nc of n, and for the other, we have to sum over nc of m. The whole thing is to relate those formulas. So for every quantity which shows up, we should have a good understanding how to express it in terms of the other guy. The Möbius function is the central object, of course, so has exactly this property. Good. Okay, so I think I should stop here. Next time we will prove, first formulate the statement which tells us how the cumulants for the capital A's and the cumulants for the little a's are connected, but actually for this we need a bit more of structure of the poset of our non-crossing partitions. So namely, it turns out that the non-crossing partitions are not only a poset, but they are actually a lattice. And a lattice is a poset which has some extra structure, namely for each two partitions I have a maximum and a minimum. So we already have seen we have a maximal element for everything and a minimal element for everything, but more is true, namely whenever we have two elements, you find exactly one which is bigger, the smallest one which is bigger than both of them, and you find exactly the largest one which is smaller than each of them. And this is a minimum or maximum or meet and join, and with this it will be very nice to formulate the condition which connects the two cumulants. Good, but I think I'll stop here today.